Today, we're digging into a fantastic scientific puzzle, the planet Mercury. You see, Mercury is a world of crazy extremes, and it seems to break the laws of physics. But one challenger theory out there claims it has all the answers. So, let's get into it.
So what's the big deal with Mercury? Well, a couple of NASA missions, Mariner 10 and Messenger, sent back data that gave scientists a huge headache. They found a couple of massive contradictions, things that just don't make sense with our standard models of how planets are supposed to work.
Okay, first up, there's the ice. Mercury is the closest planet to the Sun, right? Its surface can get up to 700 Kelvin, we're talking over 427 Celsius or 800 degrees Fahrenheit. It's a furnace. And yet, somehow, we've found water ice tucked away in the shadows of its polar craters. I mean, how is that even possible?
And then there's the second mystery, its magnetic field. Now, to have a magnetic field like Earth's, you need a hot, churning liquid core. But Mercury is so tiny that its core should have cooled down and become solid billions of years ago. So, why does it have a magnetic field at all? And why is it so incredibly weak?
And look, this wasn't just a minor surprise. It completely baffled the scientific community. You can really hear the shock in this quote from Dr. David Blewett at Johns Hopkins, who just said, "Who'd have thought that?" It really captures that feeling that maybe everything we thought we knew about hot, rocky planets was just wrong.
Now, this is where the author of our source material, Mathis, comes in. For him, these aren't just little problems to be solved. He flat out claims they show that the mainstream models are left in tatters, totally unable to explain what we're actually seeing. And that really sets the stage for a completely different kind of explanation.
And that explanation is something called the charge field theory. The author basically suggests that our whole understanding of physics is missing a key piece of the puzzle, this universal field of energy particles that he calls charge.
The central idea here is something he calls charge recycling. So in this model, planets and stars aren't just sitting there in empty space. They're constantly soaking in and spitting out particles from this field. And the author argues these particles are actually photons, the fundamental particles of light. They get pulled in at the poles and then shot back out from other places.
Now here's where it gets really interesting. The theory says that when photons are emitted from a planet or star, we feel that as heat. But, and this is the key, when those same photons are being taken in, they actually cause a cooling effect. It's a total flip of how we normally think about energy and heat.
So, keeping that idea in mind, incoming particles cause cooling, let's see how the author uses this to tackle that first impossible puzzle, how you can have ice on a planet that's basically an oven.
So, just to be clear on the problem, even if the ice is in a crater that's always in shadow, the planet itself is still incredibly hot. Normal physics says that heat should travel right through the rock and just melt the ice from below. There's nothing in the standard model that would stop that from happening.
But here's the proposed solution. According to the charge field theory, Mercury's poles are basically giant cosmic vacuum cleaners sucking in these photons. This constant flood of incoming particles actively cools the poles. And not only that, this stream of particles acts like a shield, physically blocking the heat from the rest of the planet from getting to the poles. So the key takeaway here is, it's not just the shadows keeping it cold, it's an active cooling system.
All right, so that's the theory for the ice. But what about that strange, weak little magnetic field? Let's take a look at how this theory claims to explain that one.
So once again, the conventional problem all comes down to the core. Mainstream science says you need what's called a dynamo, a churning liquid metal core to create a magnetic field. But Mercury is just too small. Its core should have gone cold and solid eons ago. So the very existence of the field is a huge mystery. The author's solution? Just throw the whole core idea out the window. He argues that magnetism isn't generated from inside the planet at all. Instead, it's created by the planet's spin as it moves through the sun's larger charge field. In this view, magnetism isn't an internal thing. It's an external effect caused by the planet's environment and its own rotation.
Okay, so that's a cool idea, but does it actually work? Can you test it? Well, using just a few numbers, the planet's spin, its size, and how far it is from the sun, the author calculates what Mercury's magnetic field strength should be compared to Earth's. And the number he comes up with is 1.06%.
And here's the punchline. He says this number, which he got from just 2 simple lines of math, is a near-perfect match for what we've actually measured, which is about 1%. For him, this isn't just a lucky guess. He sees it as proof that the theory is on the right path.
But hold on, there's one more piece of the puzzle that the author uses to connect everything together, and it comes from looking closely at Mercury's poles, which reveals something really, really strange about the planet.
Get this. Data from that Messenger spacecraft showed that the magnetic field at Mercury's poles isn't symmetrical at all. The opening at the South Pole, where the field opens up to space, is a whopping 4 times larger than the one at the North Pole. And the author points out that mainstream models have absolutely no explanation for this huge difference.
But the author claims his theory explains it perfectly. He argues that the charge field itself isn't perfectly balanced, especially close to the Sun. It has more photons with one type of spin than antiphotons, which he just defines as photons with the opposite spin. And he believes this imbalance in the field is what's causing the lopsidedness we see at Mercury's poles.
And this is where it all clicks together. That bigger opening at the South Pole means more charge is pouring in there. According to the theory, this is what explains the exact strength and character of the magnetic field. And, at the same time, that same huge influx of charge provides the powerful cooling system that we need to explain the impossible ice. It's one single observation, the asymmetry, that solves both mysteries at once.
So, after laying out this whole case, connecting the ice, the weak magnetic field, and the lopsided poles, the author makes a pretty bold and confident claim about his work.
He doesn't mince words. He just says it. I consider my theory the default theory for the future. He's basically arguing that until someone comes up with a better explanation that solves all of these puzzles this simply, his charge field theory should be the leading contender.
And that kind of leaves us with a big question to chew on. We've just walked through a theory that goes against some of the foundational ideas in planetary science, but it claims it can solve huge puzzles with simple mechanics and make accurate predictions. So what does it actually take for an idea that's this different, this much of a challenge, to go from the fringe to the mainstream? What kind of proof do you need to actually rewrite the textbooks? Something to think about.